we promised before starting a new week lecture series, we'll be again revisiting whatever we have presented to you and try to add some value to it. Okay, please understand this whole module, generally in a regular university you finish in 4 months or around a semester, and we are trying to pump it very fast. So it is explicitly important that we must revisit and gradually add value to a basic concept, right? So that's why I personally prefer this Mann Ki Baat session to be one of the important sessions where not only I improve myself, also you get improved, right? Let us go back what we were discussing on the second week lecture, that was primarily thrust equal to drag, lift equal to weight. We're trying to do cruise and we drew an airplane, thrust, drag, then lift, and then weight. Okay? I was discussing with one of my students, and he was a little disturbed. He said, "Sir, you are too fast." I said, "Why?" "Well, you are drawing this diagram, lift equal to weight, thrust equal to drag, without mentioning the point of application of this thrust, drag, lift, and weight. So that will give a wrong picture to the student, especially to the newcomers. So why don't you add a little more and unfold so that newcomer can understand what exactly it means?" I agreed. Now let us see. I think he raised a good point. Let us see a typical airplane. This schematic of a typical airplane, right? And when it is flying, actually what is happening? You see, this portion gives the thrust, okay? Weight is here. Then lift on the wing will be some point, let's say here. I will explain you where exactly this point will be. Similarly, lift on the tail will be somewhere here. I say lift on the tail, lift on the wing, then drag on the tail, drag on the wing, and drag on the tail. Let me repeat. This is the point of application of lift, wing, lift tail, drag tail, and this is the weight of the overall airplane. This is the thrust. Okay. So immediately a question came, where should I represent this lift acting? On the wing as well as on the tail. In a quick and in a short explanation or more of information, let us see this aerofoil, a general aerofoil. Because of the pressure differences, you know, there is a lift. Okay? And we try to talk in terms of CL. And if you take different point, this net force will generate different type of moment, isn't it? Nose up, nose down, whatever it is, depending upon where is the resultant and where is the CG. Now what we do, we want to represent the CL and CD at a particular point, fixed point, and we ask a question, is there such point which doesn't change with angle of attack? So that I can simply write, draw an aerofoil, and I write, okay, this is the point, this is CL, this is CD, and whatever moment is there, I write CM. We have not discussed about CM, but you take CM as pitching moment, coefficient. Okay. It so happens for general aerofoil, there is a point along the chord of thin aerofoil. At that point, the pitching moment, right, is independent of angle of attack. That even if the angle of attack changes, the pitching moment about that point doesn't change. I will repeat again. See, this is the force out of this pressure distribution. So if I take pitching moment, a moment of that force about any point on the chord, they will vary. They'll vary with angle of attack also, right? For example, if I choose one point here, the resultant will give some pitching moment. If I change the angle of attack, the lift distribution will increase. Lift will change, the pitching moment also will change. However, there is a point which is we call quarter chord point. Typically for low speed, which is also called basically aerodynamic center in general. It so happens for low speed that aerodynamic center is at quarter chord, 25% of the chord. What is this aerodynamic center? It so happens the pitching moment is independent of angle of attack at the aerodynamic center. Okay? So that is why we always represent CL, CD, CM, all these coefficients at aerodynamic center. Okay? So now if I come back, I know this is the wing, so I find the chord, and this point will be 25% of the chord, so I know this point. Similarly, I know this point for tail. I know thrust, where it's located. I know where is the CG and the weight. But when I'm writing this equation of motion, remember equation of motion? From there we got thrust equal to drag and lift equal to weight for unaccelerated flight. There we are using point mass model, right? Okay, I mentioned that. Point mass assumption. That is, I am not bothered about mass distribution because I am only bothered about rectilinear motion. So I am assuming the whole mass is concentrated at the CG. Okay? And whatever we are writing, lift, weight, thrust, drag, all are assuming that these forces are being applied on that point mass. Okay? But I know in reality lift is not acting at CG, this lift is not acting at CG, this thrust is not passing through CG. So what is done? Very simple. If I have a force here, if I know this is the CG or any other point, I can transfer this force here and a moment. Of course, I have seen the moment side as a positive by convention. If it is negative, the value will be negative, right? Okay. So I can transfer a force from one location to another location using force and a moment. So what is done is all these forces, lift tail, lift wing, all drag, etc., are transferred to CG here. Also the thrust force, and whatever moments are there, they are also transferred. But in this analysis, it is assumed that all those moments are balanced by elevator, trimmer, or whatever it is. When I am writing this equation of motion, it is a point mass model, and the assumption is all the moments are balanced, and it's a stable flight. Okay? So this clarity must be there. Then we were also discussing about rate of climb, and we have seen that rate of climb is related to excess power. But one thing I must tell you, for this sort of unpressurized airplane, aerodynamically their ceiling or service ceiling altitude will be much higher than actually you can fly this machine for other conditions. For example, if you are going above around 9,000-10,000 feet, the oxygen level is reduced. So you need to carry oxygen cylinders. It's very uncomfortable for pilots. And beyond that, if you go, there are naturally problems which are more specific to a case where the airplane is unpressurized. Okay? So for all practical purpose, the service ceiling and absolute ceiling, whatever aerodynamically being predicted, and operationally what we do, they are being limited because of these primary reasons. Okay? So that is what I need to mention you on that. And then we also very explicitly talk about thrust required, and we are talking about CL by CD, and we gave a statement that it means CL is under root CD naught by K. And we will try to add more values on this CD naught and K, and we'll try to see how can I get these values even through flight experiment. Okay, that's the final thing. Get it from wind tunnel, do a flight test, then see they are close or not, then you say yes, this is the value. Okay, so these are the things we will be doing. Okay, thank you.
Cessna 206 fully glass cockpit, 300 bhp brake horsepower. This is called is PFD, MFD. Primary features, main features. Okay, called arm standby battery, master avionics, that is called throttle, mixture, propeller pitch, control column. Okay, pitch, aircraft is moved, backward pressure, aircraft goes up, down, aircraft goes down. That is ailerons, left or right. You can turn left, you can turn left wing below the horizon, right wing. If you press right, then right wing below the horizon, left wing up the horizon. Okay, called two rudders jointly. Okay, then we can start. Press arm, then battery, and that is your standby instrument in case main, primary and main are failed. That is called standby. Altimeter, artificial horizon, airspeed indicator, or artificial horizon altimeter. That is called PFD. Okay, that is manifold pressure, RPM, all readings. Your engines, oil pressure, temperature, CST, EGT, airspeed, altimeter. Now mixture in, throttle half inch in, fuel pump on, then fuel pump off, mixture out, then crank ignition, right, left, both, then start. Now engine start. Now alternator on, avionics, beacon, nav, stop.
Today we'll experience the flight of Cessna 206H. That's registration is VTIIT. The aircraft has been visually checked with a go-around inspection, and now we're going for the ground run, after which we'll experience the climb, takeoff, climb and the landing of this aircraft. Inside the instrument panel, you can see he's checking for the flaps, the different positions of the flaps, the various readings on PFDs and MFDs. The aircraft is being warmed up and is being ready for taxi.
Indian Tango clear to enter 27.
This is the RT voice for clearance. You can see the various engine readings on the PFDs, the oil pressure, the oil temperature, the CHT, EGT. The readings on MFD, the multifunctional display. controls are checked for free and correct movement. Cowl flaps are open. Flaps are being sent at 10 degree position for takeoff.
Lamp set for 10 degree, trimmer set for takeoff, falling flaps for setup, rudder trimmer set for takeoff.
Elevator trim and rudder trim is being set for takeoff.
Fuel on board.
Fuel selector is on both. Fuel is being taken on from both the tanks. Just keep a watch on an ASI and altimeter as we climb. Backdrop between the two magnitudes should be within the limit.
Now we can increase our throttle, airspeed alive. After airspeed, maintain aircraft 60, then slightly backward pressure. Okay, the nose goes up. This is a climbing motion. Okay, airspeed alive.
This is the airspeed. The miniature aircraft on artificial horizon can be seen. The aircraft is stable, so the miniature aircraft is also stable on the gauge on artificial horizon.
Aircraft is engaged fully on the pilot.
The aircraft is engaged fully on autopilot. The controls can be left free when the aircraft is left on autopilot. This is the airspeed of the aircraft, you can see.
That is your airspeed. Minimum. Aircraft is level.
The speed is straight and level flight. The airspeed is giving in knots. You can see the variable RPM of the engine. The oil pressure from the green range, the oil temperature between the minimum and the maximum limit. See the miniature aircraft and the artificial horizon as the aircraft is banking towards the right. Just keep a watch on the airspeed of the aircraft. See at 2300 RPM we have a manifold of 21.6 inches. We are making an approach for landing.
India
runway. See the altimeter. Airspeed reduced. Power is reduced. And here is the touchdown of the aircraft. Strobe lights off, nav off, avionics off. And finally master off.